Okay, so now that you can plot points in a polar grid, we want to now begin to actually plot polar graphs. I know you're thinking you already know how, but all you know how to do is plot individual points. But just like plotting points in a linear equation eventually leads to a line if you plot enough of them, polar graphs have their own special shapes. I'm going to give you some fair warning. Polar graphing is very tedious, but it's totally worth it because the graphs are really cool. So let's get going. First thing I'm going to need is an equation. So if I have r equals the sine, nope, that's not the one I want. R equals 3 times the sine of theta, what would the graph look like in a polar graphing situation? Cool, because we know what y equals 3 times the sine of theta looks like, right? That's a periodic curve on a Cartesian plane, but this is r equals 3 times the sine of theta. So let's get some tools. I definitely know that I'm going to want a place to graph it. So I'm going to want to work way bigger than this. I'm going to make it big because I like it that way when I'm trying to see these angles around the outside. And I'm going to want a calculator. I use a graphing calculator, TI-89. You can use a different graphing calculator or just a scientific calculator is fine. You're going to find that you want approximate values, not exact values, because we know that when we plug, for example, pi over 4, 45 degrees, into the sine function, we get root 2 over 2 times 3 is 3 times root 2 over 2. Where on earth is that? Which ring would that fall on? 3 times square root of 2 over 2. That's crazy. So we're going to want to get approximate values so we know exactly where we are on the rings. Okay. Next thing, I'm going to have to set up my graphing calculator to be able to work in polar graphing. First thing I want to do is go to the mode, and instead of having a function graph, I want it to be a polar graph. And that tells my calculator to graph in polar mode. Also, polar graphing is done in radians on the calculator. So I have to change the mode on the calculator to radians, and then I'm finished there. If you go to your y equals now, you'll notice that it's in terms of r. And I've already put, oh, I haven't, I've put a different function in. I was playing around earlier. So 3 times cosine of theta. I'm going to change this to our new function, which is 3 times the sine of theta. All right, so I have 3 times sine of theta. Now, theta is here on my calculator, and I use theta. When we were dealing with trigonometric functions, we would often change theta rather than doing the second function or the diamond and trying to get that button. We would just choose a variable x. But remember, those were y functions in terms of an angle, and any variable would do. But these are polar graphs. I have to use theta. If I don't use theta, and let me go ahead and trade that out to show you what'll happen. So I'm going to back that out. I'm going to put in x, hoping that that works. And it worked just fine. So then I go to graph it. Oh no, undefined variable. So if you get that, that just means that you need to go back, and that's my error message. Go back and put theta into your function. And I'm pretty sure I'm forgetting to tell you something, but it's definitely going to pop up while I'm working, and I'll be able to explain it when I get to that. So the next thing I want to do is look at what would this kind of a graph look like. So before I actually plot it for us, I want to look at it. So when I ask it to graph, it gives me a circle. That's weird, isn't it? You wouldn't think that you would get something off center like that, because if you're dealing with radiuses that center around the pole, why doesn't it make a circle centered around the pole? Well, we're going to see in a minute why that's true. And the other thing that we want to look at, is how to use a table with these functions. So sometimes you've used the tables before. I already have a function set up. So if I choose diamond and table set, well, what just happened here? Let's see. Diamond table set. There we go. So I want to start my table. I want to set up my table to start at the angle 0. So it's already where I want it to be. That's because my first angle that I use when I'm used to working with angles is the 0 angle. So I want to start with values of 0. And then here I can put in any value here that I want to chunk forward for each element in my table. So if my input was 1, and then I want the next input to be 2 and the next input to be 3, I would make my delta table, or my increase for each input value, 1. But I really want to make my increase for each input value, I want to make it, well, I don't want to look at, there's nothing that will take me from 0 to 30 degrees, then to 45, then to 60. I could do just like the table does. I could do 15, 30, 45, 60, 75, 90. That's totally okay, but I don't really need all those values, so I don't want to play with them. So what I want to do instead is scroll down here and choose independent variable. Instead of it being auto, I want to make it ask. That means the calculator is going to ask me for my theta value each step of the way. That also helps me organize my table when it's in decimal form, because I'm not really used to looking at theta values in decimal form. So I have that, and that was the last thing I was thinking of before that I needed to find out. All right, so now I'm going to go home on my calculator, and I want to set up my table. So setting up my table, what I mean is I want to choose a theta value, that's my input, and then get out of that whatever my r equals 3 sine theta is. So let's start with the obvious first choice, which is theta equals 0. So the sine of 0 is 0 times 3 is 0. So I know that my first point, the point along the 0 angle, my first point is going to be at 0. So the radius is 0 on the angle equals 0. Okay, my next value I want to put in, I really want to put in 30, not 15. We like our common angles. So I want to put in 30, only I'm going to use radians for that. So for 30, I have pi over 6. This one's easy to do without the calculator as well, because the sine of pi over 6 is 1/2. And 3 times 1/2 is 3/2, or 1.5. So I know that the next point on the angle for 30 degrees, or pi over 6 degrees, has a value of 1.5. Well, let's label our axis first. So if I go 0.5, 1, 0.5, 2, 0.5, 3, 0.5, 4. So 1.5 would fall right on this circle on the pi over 6 axis. So the next point on my graph would be right there. So the next input value after the common angle pi over 6 is pi over 4. Okay, this one gets trickier. The sine of pi over 4 is the square root of 2 over 2 times 3 is 3 root 2 over 2. Where does that fall? We're really going to want to have a table, or we want to have a calculator to figure it out. On any other scientific calculator, just plug in sine of pi over 4 and then multiply that by 3 and you'll get a decimal. If you want to use your table function, oh, that was table set. There we go. If you want to use your table function, you want to come down here and look at, well, here's my 0 equals 0. Yeah, that's right. The next one I put in, pi over 6. I've already done this, obviously. Pi over 6, that's the approximate value for pi over 6, and 1.5 was my output. So my next one, I don't want to assume that my next one is pi over 4, because I don't really remember what I was messing around with when I was messing around with it. I'm going to go to the next place in my table. I'm going to press enter, and it takes me down here, which means I can ask it to tell me the value for this function, because this function is already stored right here. If theta is 0, R1 And the function, the only one I have stored under R1 is 3 sine theta. So I'm going to put in this time pi divided by 4. And now, oh, I don't want that. So that's my input value, and my output value now is 2.123. So still not perfectly aligned with one of my circles, but definitely easier than looking at 3 root 2 over 2. I have no idea where that is. All right, so let's see. Let's go ahead and plot this one. On the 45-degree ray, I'm looking at 2.13. So here's my 2, just a little bit more than 2. Okay, let's go to the next one. My next common angle is 60, or pi over 3. So I'm going to ask it to ask me. Okay, pi divided by 3 is 2.5918. So on the pi over 3 ray, I want to find 2.5, a little bit more than 2.5. So here's the 2.5 line, and a little bit more than 2.5 is sort of right there. And you can almost see that circle that we saw, right? You can almost see it starting to sort of shape itself in the polar graph. Let's go to our next common angle, pi over 2. I think this one might be easy because the sine of pi over 2 is 1 times 3 is 3. Oh, that one was easy. So let's take it right over here to 3. And if I were to connect these, they would make that half of the circle. But does the other side come back? And what about all these angles down here? What happens then? Let's just keep going and have a look. Our next common angle, 2 pi over 3. And I'm going to come down here, ask it to, these buttons are so tiny for my old lady eyes, 2 pi divided by 3 is 2.5981. So now I'm looking at hey, check it out, 2.5981, that's the same value I got there. 2.59, oh, 18, I'm sorry, I said that backward. 918. So that means this point is going to be right here. It's going to be sort of a mirror of the other point. Hey, that looks like some kind of symmetry going on. In fact, I'm going to spare you the suspense. It's definitely symmetrical. So on the second quadrant, 45-degree angle, reference angle in the second quadrant, I'll get the same output value. So it'll fall right, if I can figure it out there. And on the reference angle for pi over 6, I will get 1.5. All right, and so if I complete that, I get what appears to be a circle, and indeed it is a circle. And if I go back to my graph, I can trace it. I've moved it down so it doesn't bump across the top anymore. I can see that it's clearly here. I can trace this graph and see that indeed the height of it is at y equals 3. And by continuing around the circle, I can see that it's at its widest points. I'm looking at an x value of negative 1.5. And at its other widest point, an x value of 1.5. And at an elevation of 1.5. And that just means that on the Cartesian plane for this polar graph, I have a circle symmetrical across the y-axis or over the y-axis that has a radius of 1.5. Half, by the way, that. You might also be wondering, I've only gone halfway around the unit circle, or I've only gone halfway around the circle, so trying to figure out whether we're talking about this circle or this circle, it can get a little confusing sometimes. I've only used angles from 0 to pi. Ah, there we go, that was easy. By the way, if I had plugged in pi for this angle, pi, sine of pi equals 0 times 3 equals 0. And so I just end up right back in the same point. Just throwing that in at the end. But why don't I go beyond pi? Well, remember, all students, right, take calculus, at least the good ones. I only have positive radius values in the first and second quadrants. In the third and fourth quadrants, I get negative radius values. But what is a negative radius in polar coordinates? It's just the opposite. So I would get a negative value. I'd get a negative value over here, but a negative tells me just to take it right back there. My next angle would give me a negative value here, but the negative radius on this angle, I'd get a negative value, which just tells me to take it there. Same thing all the way around. I'd get negative values all the way around, but when we plot the negative point, we always just go straight across. And so I would just end up repeating myself, going around the same circle again if I continued into the third and fourth quadrants for input values. Okay, one more thing before we call it a day, and that is to talk about the fact that polar graphs have symmetries. So let's look at, and I think I can do this without having to pull up a bunch of graphs or a bunch of tables. So the one we just saw appears to be a circle centered about the line pi over 2, or the ray pi over 2. This would be pi over 2 symmetry. Or symmetry with respect to the line theta equals pi over 2. You're going to have symmetries around the x-axis. So you'll have shapes. They're not all circles, by the way, but that's where we're starting now. We've got a couple more units on this, or a couple more lessons on this unit. So you're going to have shapes that are symmetrical over the x-axis. If it's on this side, that's symmetry with respect to the angle theta equals pi. If it's over here, let me change the color. If it's over here, it would be symmetry with respect to the line theta, or the angle theta equals 0 or 2 pi. And if you get a symmetry down here, then it's symmetry with respect to the angle theta equals 3 pi over 2. You can also get a symmetry with respect to this line. So if you have something that has, for example, this shape, this would be theta, or symmetry with respect, that's a mistake, symmetry with respect to the pole. So not the origin, but symmetry with respect to the pole. Now, a couple extra comments for clarification when we're talking about polar graphs. So this was an overview. This has a special name because what do we call this line or this ray in polar graphing? We call it the polar axis. So this is actually symmetry. I know I wrote it, now I'm going to cross it out. Symmetry with respect to the polar axis. And last but not least, we can talk about all of these symmetries in terms of points that exist on the graph. For example, theta equals pi over 2 symmetry. If you have a point r theta on the graph, then for this symmetry, you would be guaranteed a point that reflects across theta equals pi over 2, and that you would be guaranteed a point r is the same. Theta is on the opposite side, so we'll use the reference angle from the x-axis and say that theta is pi minus theta. So if the r theta is on the point, if the point r theta is on your graph, then you know you have symmetry across the line, the angle, theta equals pi over 2, if you also have the point R, pi minus theta. Easier said than done in lips. Easier done than said. Holy cow, I can't even tell a joke anymore. All right, same thing over here, down here, same values would apply. Over here, if you have symmetry with respect to the polar axis, then for any point r theta on the graph, you would have the reflected point, r stays the same again, and theta is just minus theta. You just took theta in the opposite direction. And symmetry with respect to the pole, given any point r theta on your graph, you would have the point r and pi plus the same reference angle, pi plus theta. There are also a couple of other values that you can use. They're written in your textbook. I don't think we'll be using them, but they have more to do with the coordinate planes. I'm going to give them to you just so you see them. The other way of looking at this could be minus r, so you're looking in the opposite direction, and theta. So the same theta angle, just the minus direction, minus r theta. Same thing over here. This could be written instead as minus r minus theta. And in the case of origin about the polar axis, you get, oh, I made a mistake. I gave you that one already. And in the case of symmetry about the polar axis, you would, oh, I already gave you the wrong one, the other one. Hang on, I hope I didn't confuse you on that one. So this would be r minus theta if I use the designation of, I have a radius, right? The same radius and just opposite angle, or the same radius, but we would be up here. So it'd be pi minus theta, right? To get me to this angle up here, the reference angle here, but r would be negative to push me back over here. Okay, so I know the symmetries are a little tough to think about. They were tough when you were just talking about polynomials, but they can be a little bit tougher when you're talking about these. We're going to evaluate these in a very global way in the beginning, and then we can start looking at maybe developing some more solid concepts of symmetry. So that's the beginning of polar graphs, which make really cool shapes. They use really cool calculations to make those shapes, even though the calculations can be a little tedious.